All right, today we're going to decode a secret language. It's a language engineers use to talk to complex systems, to understand them, and ultimately to control them. We're talking about frequency response analysis, and trust me, this old school technique is more important for our future than ever before.
So let's just jump right in with a big question. How do you make sure a rocket flies straight? Or that a self-driving car doesn't suddenly swerve into a ditch? How do you guarantee that these incredibly complex, high-stakes systems are going to behave the way you want them to without shaking themselves apart or just spiraling completely out of control? Well, that is the core problem we're going to unpack today.
This isn't a new problem at all. If you go way back to the 1930s, engineers like Harry Nyquist and Bode were wrestling with this exact same thing. They needed to know if their brand new telephone amplifiers would work reliably or if they would just catastrophically fail. And they had to know this before they spent a ton of money actually building them. So what did they do? Well, their solution was just brilliant in its simplicity. Instead of hitting the system with a bunch of random, chaotic inputs to see what would happen, they chose the simplest, most pure, most predictable signal you can possibly imagine, a perfect sine wave.
It's kind of like giving a machine an eye exam, right? The doctor doesn't show you a complicated movie scene to check your vision. No, they show you simple, clean, repeating patterns, letters on a chart. And by seeing how you respond to those simple patterns, they can figure out everything they need to know about how you see the world. It's the same idea here.
So here's the core idea. We send in a nice, clean sine wave at one specific frequency. We let the system settle down for a second, and then we measure the wave that comes out the other side. Then we do it again at a slightly higher frequency, and again and again. We sweep through this whole range of frequencies, and by doing that, we build a complete profile of the system's true character. And here's what's so wild. For a whole class of systems, when you put a sine wave in, you get a perfect sine wave out at the exact same frequency. That's it. The only things that change are its size, what we call the amplitude, and its timing, which we call its phase. So really, these two measurements, they're everything. At every single frequency we test, we just ask two simple questions. Did the signal get bigger or smaller? And did the signal get delayed or maybe even pushed forward in time? The answers to just those two questions across all frequencies contain all the system's deepest secrets. Okay, so we've run all our tests. We've got pages and pages of data. Now what? How do we actually make sense of all of it? Well, we use an incredibly powerful visualization tool called a Bode plot. A Bode plot, named after Hendrik Bode, of course, is just a brilliant way to see all this data at once. It cleverly splits our two key measurements onto two separate graphs. The top graph shows you how the amplitude changed, and the bottom one, that shows you the phase shift. And both are plotted against the frequency we tested. Simple as that. And this is where the real magic of Bode plots comes in. You can take a really complicated system model, break it down into a few simple, basic parts, sketch a few straight lines for each of those parts, and then you just add them all up. And the result is a surprisingly accurate picture of how the entire system behaves. It lets an engineer see just at a glance where the system might start to shake or get sluggish. Now, the Bode plot is fantastic, no question, but you're still looking at two separate charts. So you might be thinking, what if there was a way to see the relationship between amplitude and phase in a single, unified view? What if we could smash them together? Well, that brings us to our second amazing tool, the Nyquist plot. This thing gives us a completely different perspective, and it combines both of our measurements into one single, powerful map. So, instead of two separate graphs, a Nyquist plot uses polar coordinates. Think of it like this. For each frequency we test, we draw an arrow from the center of the graph. The length of that arrow, that's our amplitude. And the angle of the arrow, that's our phase shift. As we sweep the frequency from low to high, the tip of that arrow traces out a unique path, a unique shape. And here is the mind-blowing part. That shape, that one single curve traced out by the tip of our arrow, it contains every single piece of information we need to know to determine, with absolute mathematical certainty, if our final system will be stable or if it's going to be catastrophically unstable. The entire secret, the key to this whole puzzle, it all revolves around one lonely little point on this map, the point at -1. That's it. That's the critical point. That is the danger zone. This is the famous Nyquist stability criterion. It's a really profound rule that basically says we can test a system in a simple state, draw this one picture, and from that picture alone, we can predict exactly how it's going to behave in its final, more complex form. And it all comes down to that plot's relationship with that one critical point. So the rule is dead simple. You traced out your Nyquist plot. You look at that curve. If it does not loop around, if it doesn't encircle that critical -1 point, you're good. Your system is stable. It's safe. It's going to work. But, and this is the big but, if that curve does wrap itself around the -1 point, game over. Your system is unstable. It's guaranteed to fail. Encircling that point means the system's own feedback has turned destructive, amplifying tiny little errors into catastrophic oscillations. It's just an incredible insight. A simple check on a drawing predicts a complex, real-world failure. Now you might be thinking, okay, this is all very clever, but this was all developed back in the 30s and 40s. That's ancient history in the tech world. In an age of AI and supercomputers, why are we still even talking about this? Because the work done by these pioneers, it was so unbelievably fundamental. They weren't just inventing a clever trick. They were discovering a deep, underlying truth about how dynamic systems behave. Their methods are taught in every single engineering university on the planet for a very, very good reason. What makes this whole approach so timeless is just how practical it is. You don't need a perfect mathematical equation for every little component. You can just take the real thing, hook it up to a machine, test it, plot the data, and use that real-world information to design a stable system. It gives engineers a powerful, intuitive feel for how their designs are actually going to behave out in the wild. It's really a powerful reminder, isn't it, that sometimes underneath all the complexity of our modern world, there are these elegant principles and these beautiful visual tools that allow us to understand and control it all.
Thanks for joining me for this explainer.